So let me say it again. So given this Lagrangian, given this Euler Lagrange equations and these equations of motions of the Dirac field, we have to find out this Lagrangian L such that when put in this equation, this set of equation will give you this. Okay. Now, just a minute. Now, remember that the Lagrangian we want to construct, which will give you ultimately these equations of motion from these Euler Lagrange equations. Okay, sorry, Euler Lagrange equations. Just a minute, I have some internet problems. Let me fix it. Okay, disconnected. So, can you hear me?
Yes, sir.
Okay, okay. Just a minute, just a minute, just a minute. Hello, can you again just, can you hear me just again? I'll change the internet connection.
Yes, sir.
Hello? Okay, 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 thank you. Now, the thing is that this Lagrangian, which we want to construct, should be a single component object. That is the most important concern in the context of Dirac fields, because Dirac fields themselves are matrices, 4x1 matrices. And also it should be a Lorentz scalar, that is, it should be invariant under Lorentz transformation. And this thing, that when we put Lagrangian in these equations, we will get equation 33 and 34. Now, look at this Euler Lagrange equation. This is a general form of Euler Lagrange equation, but there is a catch here. One is that this Lagrangian, I said, it should be a single component object. The form of Euler Lagrange equation shows you that I am taking a derivative with respect to an object psi, which is a 4x1 column matrix. So L is a single function, psi is a 4x1 column matrix. So how you can, what do you mean by this? Okay, so we have to, what do you mean by differentiating with respect to a matrix? We have never seen such kind of things earlier. Okay, but ultimately what the point is that we have to realize this in terms of single component derivatives. Okay, so this derivative cannot be with respect to a matrix, because that derivative with respect to a matrix is not defined. Okay, so if you see very carefully what we have done while deriving the Euler Lagrange equations, we have derived the Euler Lagrange equations generally for a field, which I in my note write as chi Rx. But I have not said anything about this nature of chi Rx, because it can be scalar or vector or whatever. But when it is a Dirac field, it has a column matrix structure. Then this derivatives has to be defined. Clear? What is the problem? Now, in this derivation of this Euler Lagrange equation from action principle, we have written the action in terms of these fields and its derivatives, which I write for Dirac field in this way. Just replace chi by psi and del mu psi, and psi bar is the another conjugate field, which I have to include to make all the degrees of freedom explicit. So Lagrangian is a function of this, where these are all 4x1 matrices. Okay, so this is the action, where psi and psi bar are like this. One is a 4x1, one is 1x4. Clear? Now, remember that since psi is a 4x1, all these individual components of psi, this psi 1, psi 2, psi 3, psi 4, and here also psi 1 bar, psi 2 bar, they are single component objects, each individual component objects, they are sitting in this functional form. Okay. Now, which I express through in a compact form through Chi and Chi bar, row and column matrices. Now, if I wish, I could have written this L as this. So dependent on Chi means dependence on all these four components. So Chi alpha, where alpha runs from 1 to 4, and Chi 1, and the Chi 1 bar alpha also, this alpha from 1 to 4. Okay. Then if we apply, then all the components are single component objects. And now if we apply variation delta S, I can write these variations in terms of variations of these components instead of writing it variations of delta Chi itself. Clear? Therefore, and remember, these components, this alpha index is not a Lorentz index. This mu index is a Lorentz index because Lorentz index means it is associated with the Lorentz transformation, coordinate transformation. But alpha index is just counting these four elements. So there is no meaning of alpha up and down. I will always put alpha in as a index like Chi R as I written. This R is the just counting index for number of components here. Clear? Therefore, if given this Lagrangian, this is same as this, only Chi and Chi bar written in explicit form in terms of its components. Now, if I make delta S equal to 0, I get same form of Euler-Lagrange equations, but in this form, where for every component, I will get one such equation. Where alpha, there are 4 equations here, 4 equations here. So 8 equations. Okay, these 8 equations are written in a compact form in this set of equations. So this contains 4 equations. This contains 4 equations. Symbolically, this has no mathematical meaning. Symbolically, it captures the content of these 8 equations. Is it clear to everybody?
Okay, sir.
Okay, sir.
So L should be such a function of these components. Now I am not talking about Chi and Chi bar as compact objects like 4 cross 1 or 1 cross 4. I am speaking in terms of components. Now, once I do everything in terms of components, at the end, later I will come back to the compact form. Okay, let's see. So now the Lagrangian should be such functions of this Chi and Chi bar and their stress time derivatives, del mu Chi bar and del mu Chi alpha and del mu Chi bar alpha, such that when that Lagrangian is put here, we will get these equations. Okay. So, but these equations are written in terms of Chi. So let's write it in terms of its components. Okay. Now look at this carefully and try to see whether these equations, when I write it in terms of its components, will give you this equation, because Chi is a Chi or del mu Chi is a 4 cross 1 matrix, which contains Chi 1, Chi 2, Chi 3, Chi 4. And this is a 4 cross 4 matrix. So I multiply these matrices and write each component. So I will get this. Look at these indices. If I put an alpha beta, so there is a sum over beta, repeated index, there is a sum over beta. And so first term will give you this. Second term is just m Chi beta, m Chi alpha, which I can write also by introducing this Dirac delta function. Is it clear? Because this equation and this equation are same. Only thing is that this is the component equation, this is the matrix equation. So I just matrix equation I write in terms of its components. So here are also there are 8 equations. For every alpha there is an equation, beta is summed over. Okay, so you have to, when you read this class notes at your home, just explicitly write down slowly and thoroughly understanding what is going on. If you have any doubt, Ask your friends or ask me over phone or email, whatever. If you have some doubts, it is better if you call me, because if you want to write it, then if you just put a picture of your notebook and send it me, and then talk me over phone. It will be easier to explain. So up to this point, everything is clear. So basically, I broke down the Dirac equation in terms of components. So these are this Dirac equation for psi and psi bar in terms of its components, and these are the Euler-Lagrange equations in terms of psi and psi bar in terms of its components. Now I want to find L such that when put here, we'll get these equations. Clear? Now I am giving you. Now you have to guess what can be the form of L, so that I put it here, and will get you this. Okay, and you can guess, make the guess, or you can see these equations. Look, you can stare at this form of these equations for some time, and can use your intelligence to construct the form of the Lagrangian, which will give you these equations when put in all the Lagrange equations. And I have write down this equation directly, and you have to verify. And just verify that, put it here, put this Lagrangian LD1, D for Dirac, one form of this Lagrangian I have written, put it here, and you will see we'll get this. Now this I have written in a compact form. You could have written in terms of individual components like this. See, this is a single component object. So psi bar is a 1 cross 4, gamma mu is a 4 cross 4, it is a 4 cross 1. So 1 cross 4 into 4 cross 4 matrix into a 4 cross 1 matrix. The result is a 1 cross 1. Clear? Which you can write in terms of alpha beta in this way. There is a sum over alpha as well as a sum over beta. There is no free index, because this is a closed matrix multiplication. Okay, so this is also like this. So m psi bar psi you can write component wise this way, or also by this way, by introducing the, sorry, there is a mistake here. This should be beta. There are some small mistakes, because there are too much indices. We are in the jungle of indices. So don't get lost in this jungle of indices. Always, after you do some calculations with the indices, then pause yourself, take a pause, and go up and give a bird's eye view on the everything, what you are doing. And then again, sink into this sea of indices and proceed further. And then again, go back and see what you are doing. So frequently you have to do this. Otherwise, you can't feel what is going on. Okay, and you can't also feel unless you do the calculations. Okay, so you check that the above Lagrangian in equation 39, which is in this form, when used in Euler-Lagrange equation 35, which is the Euler-Lagrange equation 35 is this equation. Okay, in the first equation for psi alpha. When you put this Lagrangian in psi alpha, you will get this equation for psi, equation 38 for psi beta, psi bar beta. And when you put this equation in the other equation, in this equation for psi bar, you will get the equation of motion for psi. The same thing you got, same way you got it for phi and phi star for your complex Langevin field. That also for this, you put the Lagrangian in the equation for phi, you will get the equation of motion for phi star. And if you put the Lagrangian in the equation of, in the other Lagrange equation for phi star, you will get the equation of motion of phi. Clear? So you can get that. Is it clear? You can ask me if you have any doubt. ঠিক আছে?
Okay, sir. Yes.
Okay, so basically, so what we have done, basically this is the bird's eye view. The Dirac Lagrangian we derived, it is of this form. You can check that this Lagrangian is a single component object because all these products are matrices, but their orders are synchronized in such a way that the product is a 1 cross 1 matrix. And the Dirac equation is this. So all the information content of this Dirac equation or this Dirac equation, these two Dirac equations you have to mention so as to express psi and psi bar. All these two Dirac equations correspond to this Lagrangian. Now you can forget about all Lagrange equation and can to investigate properties of the Dirac field. You can either investigate the solutions of this Dirac equation or directly this Lagrangian. Okay. Solutions you need to understand any specific property, how it is Dirac equation, how
Hello,
that.
sir. You are not audible properly.
Just a minute.
You are audible, I think. I can hear you.
Hello.
Yeah, we can hear you.
Yes, sir.
Okay, Raptosha, check your device. Okay. So if this this is the Dirac equation and this is the Dirac Lagrangian. So we also obtained Klein-Gordon equation and Klein-Gordon Lagrangian earlier, both for real Klein-Gordon field and both for complex Klein-Gordon field. Now we have obtained it for Dirac field also. Now let's look at the form of the Dirac Lagrangian here. Now I am doing some calculations. So just look at it. So this is this form of the Dirac Lagrangian we derived. Now see that I can write this Lagrangian in this way. This I by 2, I can write I minus I by 2, rest same. Now this I multiply. So the first term gives you I into this term. Second term gives you minus I into this term. Okay, and this rest same. Clear? Now keep this term and couple these two terms by common, take common minus I by 2 common, and you have this 2 and minus psi. And then you can see that this term and this whole term in the third bracket can be expressed as a total derivative like this, because gamma is a constant matrix. If you derivative it, in one term you will get this derivative, in another term you will get this derivative. Clear? Therefore, you can rearrange them and write the first term, the third term in next, and this derivative term. So I can write this whole thing, whole expression as by the symbol LD2 and this, where LD2 is just this. Now, this Dirac, I showed that this serves the purpose of Dirac Lagrangian. It gives you Dirac equation when put in equations of motion. Now, this equation has a part, this Lagrangian has a part which is a total derivative, and you know that any term which is a total derivative according in the form of a total derivative, total divergence in the Lagrangian can be dropped because it will not affect the equations of motion. Clear? Or given in Lagrangian, you can add also a total derivative term to make your expression smoothly looking. It will not change equations of motion. So in other words, this Lagrangian, this expression LD2 is an equivalent Dirac Lagrangian. Can you get this point? If LD is a Lagrangian and I have written it in terms of LD2 minus a total derivative, and a total derivative term gives you no contribution in the equations of motion. Therefore, LD1 and LD2 both will give same equations of motion when put in Euler-Lagrange equation. Therefore, I can say this is another form of Dirac-Lagrange. Is it clear?
Yes, sir.
Hello, sir.
Yes.
I had a question related to this, but not directly connected here. Suppose we are deriving the Euler-Lagrange equation by extremizing the action, and there we have this del mu total derivative term. So we can turn it to zero in spatial limit, but what to do with the time?
When you apply variational principle, action minimum principle, then that and take the variation, then you look at this derivation of Euler-Lagrange equation in which you are pointing. Let's go back to the derivation of Euler-Lagrange equation. Where it is here. So when you take this derivative, you see a term like this came. Okay. When you take this just delta of L, so if there is a total derivative term in L, a term like this will come, and when you integrate to find this before x, to find this, to apply this, to find delta S or to make it zero, this integral involves integration of this over all space, and that integral should vanish because of the divergence theorem. Total derivative of this thing, integral over all space, gives you a surface term. If you have understood this, have you understood this? Why this term vanishes in this Euler-Lagrange equation? In classical mechanics, this is the only function, or this is the only total derivative of time. In this case of fields, the space part also you have to include. So it contains all the time derivatives plus the space derivatives, total space-time derivatives, which is the total divergence. And that when integrated over d4x will give you zero because of divergence theorem, because you are integrating over d4x over all space, and if you apply divergence theorem over this, this integral will turn into a surface integral over 3 surface. Okay. Now on that surface, this delta variation is 0. And if you consider the surface to be at infinity, fields are always taken to be 0 at infinity. In any way, this is 0. So total derivative term in the Lagrangian will not contribute to the equations of motion. Equations of motion is the only comes from these first two terms. Is it clear?
Sir, I was saying that we can take special limit to infinity, but what about the time part? I mean,
take between T1 and T2, but ultimately you are taking the delta variation, because of the delta variation means what? At same time, the difference between the fields are 0. Paths are converging. Different ways of evolution of the fields are, I mean, like this. Just a minute, like this. This is T. Okay. So this is, say, S action. So here, or say for field Q, sorry. Here these Q's are these fields. Now at time, so what is delta Q at any time at time T2? Delta Q T2 is Q at T2 for this path minus Q at T2 for this path. But since delta variation means that initial and final times are fixed, whatever be the paths, then delta Q2 and delta at point T1 and at point T2, all this delta phi should be 0. You get my point?
yes, sir. Yes. Okay.
So when you take this integral d for x, it is all over space, true. So you spatial infinity, but t is finite. But that contributes 0 because of this definition of delta variation. The delta variation means paths are fixed. I mean, all paths are have the same value of field at t1 and at t2. Because of that, it becomes 0, even for the d4x integration, t part of this integration. Yeah. So both of these LD1 and LD2 can serve the purpose of Dirac Lagrangian. So we will use either forms depending on our ease of calculations in a particular context. So both forms are equivalent, equally captures all the features of Dirac field. Okay, these forms give same equation when put in Euler-Lagrange equation. So this is again the short bird's eye view or summary. This is Dirac-Lagrangian have this form, or you can take it in this form. This form you see is a bit symmetric with respect to psi and psi bar. Okay, so both psi and psi bar. So in this term, this is a bare psi bar and this is a derivative of psi. Here also that is a derivative of psi bar and bare psi and psi bar psi. Here there is in this second form only derivatives of psi are coming. Other derivative is not coming because you have dropped it by making it a total divergence. But that will not hamper this apparent appearance of symmetric with respect to psi bar, does not hamper any physical any information that is contained in these two Lagrangians. The information content is same. Okay, this term is a bit easy to handle while during calculations because it involves only two terms. So it involves three terms. Because of that, this kind of Lagrangian we often use to study the different properties of the Dirac field in terms when we want to see it through the Lagrangian.
Sir,
yes.
In LD2, there is a total derivative term del mu.
In LD2, LD2 is this.
LD1 equals to LD2 minus this total derivative term. Yes. This total derivative term is del mu psi bar gamma mu psi, and this psi bar gamma mu psi is we have
the current.
Current. Is this coincidental or is there any subtleties there?
No, actually, you can drop it because it is a conserved current. Okay, is this coincidental means? Because when you because this total derivative term, this term comes because okay, I will see. We will see because this is not coincidental. So how can I say it? How can I answer this? Let me think. Because when you see under how do you find this? So this when you say this is current, conserved current, how you find that?
We are using the normal quantum mechanical del rho del t equals to divergence of J, these types of J, not the Noether's theorem.
Okay, but if you use Noether's theorem, then you can realize why this comes. Because in Noether's theorem tells you if you make a change in phi, and then see if the Dirac-Lagrangian has to remain invariant, what kind of Dirac equation has to remain invariant, okay, then what kind of change the field can accept. Okay, now if you do that, then you will see that so that change in field will give you this kind of additive term in the Lagrangian. Because of that, you can say, okay, these Lagrangians differ by total derivatives, therefore they should give same equations. So that kind of change is a symmetry transformation of that Dirac Lagrangian, and from that kind of change you can find this out. Actually, I will, maybe I or Sanjay, when I do the symmetry transformations of the Dirac Lagrangian using Noether's theorem, then you can get it. You have to do the same calculations. Okay. So at this point, it is
okay.
Okay. So I have written down everything here. So this is here. Now the thing is that you have to check that this Lagrangian, or verify that this Lagrangian does not transform under Lorentz transformation, because that is a prime requirement of the form of the Lagrangian. Not only it has to be a single component, it has to have a Lorentz scalar, because you find action by integral over d4x. Okay. d4x integral, do you know what is the Lorentz transformation of this quantity?
It is invariant before x.
It is invariant. Okay, so L of this should be invariant, so that action becomes a pure number, space-time independent number. Okay, so we require Lagrangian to be Lorentz invariant. We obtain this form of the Lagrangian by putting this Lagrangian in the Euler Lagrange equation and seeing that Dirac equations are derivable from this. Now, so you can easily check whether this is, not easily, you have to do lots of calculations, but you can straightforward, those are straightforward calculations, but involved calculations to check that this is a Lorentz scalar. Now, I have done this calculation. I will show you these calculations, because this type of calculations I will anyway need in different, while discussing different properties of this psi Dirac field later. Okay, for this reason, just to make you familiar with what kind of mathematics or what kind of calculational tricks you have to adopt in doing algebra with Dirac fields and gamma matrices, to show that I have done these calculations. Okay. So now just concentrate on the calculations itself only. Now don't, when you look at the calculations, just be sure, just focus on the calculations only. Don't physically interpret at the very beginning. So after I do this, then you can come back and see what I have done. Okay. So this is the Lorentz transformation, standard form of Lorentz transformation. We know where this gamma should satisfy this, for this to be a Lorentz transformation matrix. So this is, so x, why I'm saying this, because x mu is there. This is del x derivative with respect to x mu. So to see its Lorentz transformation, I have to see how this transforms. Just a minute. Just a minute. Hello, can you hear?
Yes,
sir.
but you are not audible for some seconds.
Yeah, because the internet is very unstable. It's switching between two connections. Okay. So this is the Lorentz transformation matrix, and I have to see how this term transforms and how psi and psi bar transforms under Lorentz transformation, to check whether how this quantity transforms. Okay. Now I know how psi bar transforms. I know we have derived this. Psi bar under Lorentz transformation goes to psi prime x. X prime is this x prime. and this is this, where S is the matrix which in general satisfies this relation. Clear? You recall this. Now I will also make use of this fact for if this Lorentz transformation is infinitesimal, okay, where gamma mu is antisymmetric, then this S thing, this has this form, which I have derived in the class, where sigma mu nu is the commutator of this my product I by 2. Clear? These things are, you can find it in previous class notes. They are derived in this class, form of this matrix. And if for an infinitesimal, this is the form only for infinitesimal transformations. Okay, and any finite transformation can be generated by successive infinitesimal transformations. If this is so, S inverse should be like this. Okay, so I will make use of all these informations to test Lorentz invariance of this. So first thing is that I have to test how I know how psi transforms now, because psi transforms in this way with S having this property. Now how psi bar transforms? Psi bar, so that means how psi bar transforms means I have to find out how psi bar x all prime is related to psi x. That is the Lorentz transformation property, sorry, psi bar x. That is the Lorentz transformation property of psi bar. Okay, for psi x I know. For psi bar, so take it this. Psi bar by definition, psi bar is psi dagger gamma 0. That is the definition of psi bar. Clear? From earlier class. This is the definition of psi bar. Okay. Now I use this definition, psi dagger. Now I take the, now in place of psi bar x bar, I know how, what is it, because it is S psi. I take the dagger, and if to take the dagger, this they will flip. AB whole dagger is B dagger A dagger because of this. So psi bar x is related to psi or psi bar, whatever you can say, like in this way. Okay, psi dagger x S. Now look at the Dirac equation again. Look at this term first. This is an easier term. It contains product of psi and psi bar and psi. So let's see how this transforms. Psi bar and psi will transforms like this way under Lorentz transformation. All will become prime. Now this part, this first part, I can put this term, and for second part I can put this term. Clear? Is it clear?
Yes, sir.
Okay. Now, so look at this expression. You want to, I have to, so this is a 4x4 matrix. This is a 4x4 matrix. This is a 4x4 matrix. So all this product is a 4x4 matrix. This is a 1x4. Sorry, 4x1. This is 1x4. So whole thing is 1x1, which is this thing, and this is the term sitting in the Lagrangian. Yeah. Now I have to find S dagger. Okay. Let's, for an infinitesimal transformation, let's see, S dagger is this, and S dagger is this, means S dagger is 1. This dagger makes I plus I and sigma mu nu dagger, because sigma mu nu is a matrix. Now to find S dagger, I have to find sigma mu nu dagger. Okay. And what is sigma mu nu dagger? Sigma mu nu dagger is this. Sigma mu nu is by definition is this commutator of gamma nu product I by 2. Whole dagger that makes minus I by 2 and the dagger of the commutator. Minus I by 2, I open up the commutator and dagger, and minus I by 2, and then you take the dagger. So individual term will be a plus b dagger. A plus b whole dagger is a dagger plus b dagger. Okay, so this, there is no flip here. Now when in the product, when I want to take the dagger, they will interchange positions. So it will be gamma mu dagger gamma nu, and this will be gamma mu dagger gamma nu. Yeah. Now I know what is gamma nu dagger. I used this in earlier class. Gamma nu dagger is gamma 0 gamma nu gamma 0. Gamma mu dagger is gamma 0 gamma mu gamma 0. Similarly, these things. Now, so you see there is a gamma 0 sitting in front and a gamma 0 sitting at back. So take this common this side and this back one common that side. So in between you have this gamma 0 square, you put 1. Therefore, you will have this term. Okay. Now you include minus 1 inside, put minus 1 inside, and you will get this reverse thing, which is basically, again, you can write it gamma 0 I by 2 commutator. So, and this whole thing in this first bracket is sigma mu nu. So sigma mu nu dagger is related to sigma mu nu in this way, which is the same way gamma mu is related, gamma mu dagger is related to gamma mu. Okay. So now you can put this sigma mu nu dagger here in terms of sigma mu nu. So putting this, you get as dagger we obtain in this way, and this sigma mu dagger, you put gamma 0 sigma mu gamma 0 mu nu gamma 0, and you do these calculations. You take gamma 0 outside. So 1 you can write gamma 0 square. So gamma 0, and this thing. And what is this thing? This you can remember. This is S inverse gamma, because S gamma is this, S inverse gamma is plus of this. So what you obtain, S dagger gamma is basically gamma 0 S inverse gamma. Here. Okay. Buzle?
Yes, sir.
Sir,
Yes, sir.
Yeah.
sir, why we are not taking the dagger of omega?
Omega is the Lorentz transformation parameters. They are not, firstly, they are not matrices. They are just numbers. They are omega mu nu for a omega mu nu is a particular number. Is a number, and omega, they are antisymmetric. There are 6 numbers, and the 6 numbers correspond to Lorentz transformation matrix, Lorentz boost and Lorentz rotation. Okay.
Okay.
So therefore, they are real numbers.
So it is not matrix.
No, it is not a matrix.
Yes,
Sigma mu, for a given mu nu, omega mu nu is not a matrix. But for a given mu nu, sigma mu nu itself is a matrix.
Yes, sir, yes.
Okay, so these things are very crucial. So always remember this. So what is a matrix? What is a, always this just appearance of indices does
Omega
not make
matrix omega mu nu matrix element, right?
Omega mu nu is called, you can call a matrix element of the omega or Lorentz matrix. Like this is a Lorentz matrix, but this is a matrix element. Clear? This is a matrix, this is a matrix element, and this contains omega mu nu, which are also elements. You can write it this way. Okay. So, and these are real numbers because they represent Lorentz transformation or Lorentz boost and rotation. So parameters of the transformation. So they are real numbers. Because of that, there is, if it were a complex number, then we have to put star, not dagger, star, but just because they are numbers. But it is a real number. Clear?
Yes, sir, I got it.
Okay. Okay. Let me again do some internet, solve some internet problem. There is a problem again. Oops.
Now it's okay, sir. We can hear you well.
No. I am using my mobile internet, which can go anytime. So I am switching between. I mean, this home internet. This it was earlier off. It again came. So okay. So okay, let's see. So S dagger is this. So S dagger is this. Okay. Therefore, we are in a position to check this. Look at this equation 41. Here I have now I can see what it is because I know S and I know S dagger. So I have again write this equation, the same equation, transformation of psi bar psi, Lorentz transform. This is Lorentz transform form of psi bar psi, and that is this equation written earlier. In place of this, in place of S dagger, I now put this term, which is this bracketed term, and I keep psi. Okay. Now you see there are two gamma zeros here. They can be dropped because it is 1, gamma 0 square is 1. So I dropped it here and I get this term. And S inverse S psi is again 1. Okay. Therefore, I get psi dagger gamma 0 psi, and psi dagger gamma 0 psi by definition is psi bar, that is psi bar psi. That means this term does not transform under Lorentz transformation. So this term is a Lorentz scalar. So this term sitting in the Dirac-Lagrangian here, this term in the Dirac-Lagrangian is often referred as mass term because it is coefficient is the mass. So this is generally called it conventionally by mass term of the Dirac-Lagrangian. That is a Lorentz invariant term. So this term is Lorentz invariant. Now we have to test whether this term is Lorentz invariant or not. Clear? So you have to use this kind of these identities like S dagger, sigma mu nu dagger in various places. Okay, so that's why I presented it here. I could have said that Dirac-Lagrangian is Lorentz invariant, you can test, but I am doing this calculation just to build up the basic calculational schemes for our future work. Now we have to test the Lorentz transformation of this term. I do it in a very, very compact, short way. So this term is called the mass term. This is sometimes called kinetic term. Kinetic term means, this word kinetic means when there is a variation with respect to space and time. And this because of this delta mu term, derivative term, space time derivative term, this is sometimes called kinetic term. But that's a name. So the kinetic term of the Dirac equation, its Lorentz transformation is this. So all these things will get primed under Lorentz transformation. Gamma mu will remain gamma mu because gamma mu is a constant matrix. There is no coordinate transformation applied to it. Okay. Now I know how what is psi bar prime because I use this here. Psi bar prime is, I derived. Yeah, this is psi bar. This is one result. So this is one result I will use. So I use, in place of this, I use this, that result I marked. Okay, that is way how psi bar prime is transformed. Okay, and this, I know this transforms as this way. Now you multiply everything. Now S dagger again, in place of S dagger, I can use this. S dagger is gamma 0, S inverse gamma 0. So in place of S dagger, I put gamma 0, S inverse gamma 0. Clear? Now again see. Again see that this gamma 0 will go up. Oh, sorry. This term. Psi bar is this. Now I have gamma mu, this delta mu psi mu prime, that I have to form. What is delta mu prime? How this quantity transforms under Lorentz transformation? Do you know? Because this is a derivative with respect to a covariant vector gives you a derivative with respect to a contravariant vector gives you a covariant thing. So that's why this is basically this. And any contravariant object under Lorentz transformation, you can write this. You can write this for this part. For this part, you can write this. Is it clear? And for psi prime, you can write S psi. Is the second line clear to everybody? So be very careful or to know or learn that how del mu objects transform under Lorentz transformation. How this operator transform under Lorentz transformation, you can calculate it. I have taught from Lorentz transformation. Okay, so this is this case. I am sorry because I have to show you a lots of calculations, but I can't help. Quantum field theory is like this. Sorry. Now, if the second line is correct, then go to third line. Psi bar, S dagger, gamma 0, gamma mu, there's lambda mu nu. S is a constant matrix. Differentiation will not operate on this, so S comes out. So del mu just operates on psi. I can't rearrange themselves because all are matrices. If I want to rearrange, I have to use commutation relations. Clear? Out of all these things, only one thing is not a matrix, which is this. This is just a number here, because this is an element of Lorentz transformation matrix for a given nu mu. So this I can put anywhere. But other matrices, their positions are sacrosanct. I can't change them. If I want to change, just change them. If I want to change, I have to take help of commutation relations. Now, here you take psi bar and this object, S dagger, again I can use this previous relation. S dagger is this. So I use S dagger as this. Okay. And keep the rest as it is. Okay. So up to this, everything is correct, I think. Now again, lift this bracket. Psi dagger, gamma 0, S inverse. Two gamma zeros will make gamma 0 square identity. So drop two gamma zeros and directly then comes gamma mu, then this thing, then S, and then this. Okay. So this is correct. Now you see, any questions up to this line? Just look at these calculations. Any question regarding calculations? Now, group these terms. There is no harm in putting a bracket. So this bracketed term you see, can you identify this? This is the condition that S has to, this is this condition, Lorentz transformation condition, that when I say psi transforms this way under Lorentz transformation, where S has to satisfy this condition. So this is S inverse gamma mu lambda mu nu S is equal to gamma nu. So here, using that condition, in place of this, what should I write? Just gamma nu. Is it clear?
Yes,
Because
sir.
then, okay, now put this thing, sorry. So this object is psi bar with gamma, psi dagger gamma 0, keep gamma nu and this. Okay, now look, this was this form. This transformed into this and this keeps the same form. So you can replace mu or dummy indices. So mu's and nu's are same. So this quantity does not also transform under Lorentz transformation. Okay. So the kinetic term also does not transform under Lorentz transformation. Clear?
Yes, sir. But I have a question, not regarding the
Yes.
calculation.
Okay, just a minute. Yeah, just a minute. So that means Dirac Lagrangian is invariant under Lorentz transformation because Dirac Lagrangian involves only this term, product I. So I dropped I here, but in the Lagrangian I will be there. I will not transform. This term minus m mass term, that is also invariant. So I proved that Dirac Lagrangian is invariant under Lorentz transformation. Yeah, what is the question?
Yeah, in the Dirac Lagrangian there is a term minus m psi bar psi. But what do you mean by a mass of a classical field?
I don't mean anything here. Here, this I just call this mass term because this mass term, this m is not the mass of a classical field. It is a very loose way of saying this. At this point, this mass came because when I linearize the energy momentum, classical energy momentum relation, that m is this m. Now, when we will study quantum field theory, when we quantize this Dirac field, then we will see this m is the mass of the quanta of the Dirac field. After doing that, then I can say this is the mass of the quanta of the Dirac field. It is not, there is nothing called, how can a field have mass? There's nothing, that is right. Here, you will see that this m turns out to be the mass of the quanta, which the quanta means quanta has a particle nature. It's a quanta, it's a packet of energy. So that packet, you will show that this m denotes the mass of that quanta, but we have not reached at that point. Okay, so I am not saying this is the mass of the Dirac field. It is a very loose way of saying that mass term. I am saying it is a mass term. M is saying that. Clear? So actually, quantum field theory is very interesting. Once you see this quantum field theory, how you can get particles by quantizing fields. Then these objects which are defined for a particle, mass, etc., will get their meaning. Okay. Now you say if Dirac field represents an electron, electron has a lepton number. What do you mean by lepton number of a Dirac field? It has no meaning unless you get the particle concept from the field. Up to before that, you can't assign the particle attributes to the field directly. Clear? So up to this point, you don't think this is just a real number sitting here. Look at this way. But the way we derive Dirac equation, this real number in this transition from classical to quantum, that m were the classical mass. Like when you quantize a classical linear harmonic oscillator, then in the quantum version of the Lagrangian, okay, that p square by 2m minus, or p square, I mean I h cat grad square by 2m minus half m omega square x square. What this mass? What is the, whose mass is this? It is mass of that classical particle, right? Now this Schrodinger field psi, now that psi wave function. What do you mean by mass of an wave function? Now, once you quantize, came to quantum mechanics, that wave function is not a localized object. It is a field, an abstract complex quantum function, complex function of x and t. Now, when we say it is but still we just speak mass. That means it is a very loose way of saying. Okay, but the field, you can't assign field mass directly to field at this up to this level of discussion. If you want, we have to say whose mass is this, then you have to look at something more. Actually, there is a different way of defining mass in quantum field theory. We will see that. Okay, from propagator, we will see that.
Okay, sir. Okay, sir. Fine.
It's okay. So let's pause these discussions. And so this is our summary for which I told so far. So this is all these Lagrangians. You can see this is the Lagrangians for real scalar field, complex scalar field, and Dirac field has two forms. And here the equations of motions. So you can work either of them, either Lagrangian or equations of motion, depending on what you want in your investigation. Clear? So we have seen basically two kinds of fields. All these field phi and psi, phi can be real or complex, but phi is a scalar, does not transform under Lorentz transformation. Psi has a particular way of transformation under Lorentz transformation through S, and that kind of transformation is called a spinor transformation. Now, there is another kind of field. Now, these are examples of fields which are classical in the sense that they are just a mathematical function or maybe a mathematical object, not an operator. There is all the phi and psi are all mathematical functions of x and t. This has a matrix structure anyway, but they satisfies equations which are all equations of motions, which are all different. This is a different equations of motion. These sets are also different equations of motion. Okay, but all of them are Lorentz covariant. That means the aspects of special relativity are inbuilt in these equations of motion. They are invariant under Lorentz transformation, not under Galilean transformation. And we formulated this, we obtained this equation by combining relativistic energy momentum relations with quantum mechanics. Okay, because of that combination, it must satisfy the Lorentz covariant nature form of these equations of motion. Clear? Now, in nature, there is another set of Lorentz invariant equations of motion, which we have not initially derived just by combining special relativity and quantum mechanics, but they are derived directly experimentally, and those are Maxwell's equations. You know, Maxwell's equations are invariant under Lorentz transformations. Clear? They are not Galilean transformation. That means somehow in the electromagnetic phenomena, as they appear to in the world, as they manifest in this world, and the way their phenomena are studied, and their equations of motions are experimental equations of motions are directly written by Maxwell's in these equations. All these equations are invariant under Lorentz transformations. That means they are also some sort of field equations, because E and B are fields, they are functions of space-time. They are field equations whose equations of motion are Lorentz invariant. That means relativity, special relativity is inbuilt in them. Clear? But they are not, they are in this form, they are not put in this good-looking explicitly Lorentz covariant form. These forms are explicitly Lorentz covariant. Sorry, there is a mistake here. This should be lambda mu, LaTeX mistake. Now we can put this in a covariant, Lorentz covariant form by seeing this, that this B and D, you know this, but I just for completeness I am saying this. B and A, there are 6 different fields. Okay, 6 different fields means there are 3 components of E and 3 components of B connected by these differential equations. And now E and B can be expressed in terms of only 2 objects. One is a scalar potential phi, another is the vector potential A, which has 3 components. Okay, So all these Maxwell's equations, if you put this, can be written in terms of phi and a. That means phi and m, and we define an mu like this, and you can check that if these equations has to be Lagrange invariant, they has to transform, remain in form of, I mean, if they have to be invariant under Lorentz transformation, then this object composed of A and B, A0 and A, or phi array, which is related to B and D of these equations by these relations, this A mu should transforms in the same way as the coordinate transforms. Can you check this? So you should try this at home, because what is the Lorentz transformation of A mu, where A mu is defined in this way, where phi and A satisfies this, and B and D are such that these equations are Lorentz invariant. With all this series of conditions, you can see that A mu should transform under Lorentz transformation in this way. That's why we call A mu a Lorentz vector or a 4 vector. Okay. Anything carrying an index mu will not make it a 4 vector. It should transform in the way a coordinate transforms, then it becomes a 4 vector. If space-time coordinate transforms, then it becomes a 4 vector. So A mu is a vector, and A mu are functions of x and t. Okay. Now you try to write down all these Maxwell's equations in terms of A mu, because E and B can be expressed in terms of components of A mu. So ideally, you can express this in terms of A mu. Okay. Now for this, you define a object of A mu like this. Define a quantity like this. If you just define a quantity like this, it will be easier to express this in terms of A mu. And if you see, the way of definition tells you that f is a diagonal. Okay, so you check what is f. So f, different components of f you check. So for 0, 0, it is 0. It is so it is all the, sorry, it's not diagonal. Its diagonals are 0. It is antisymmetric. Therefore, diagonals are 0. And you can check 0i component, okay, ij component. So 0i component means, so 0, 1 means a1 dot minus del phi del x. And from Maxwell's equation, you can check which way, what is that? You can see that the components of f mu nu are like this. All this, it has, so it is a 16 component object, but the antisymmetry makes it 6 independent components, and these 6 independent components are 3 components of electric field and 3 components of magnetic field. So in that way, this f mu nu captures in it all these basic 6 fields, basic 6 functions, which are required to express the electromagnetic phenomena. Okay. Now you can check that because of this form, f mu nu, or we should say, you can check, if you want to write these equations, so divide Maxwell's equation into 2 parts. The last 2 are called homogeneous Maxwell's equation because of this 0 in the right hand side. These 2 are inhomogeneous magnetic equations because of this right hand side, non-zero right hand side. If you treat Maxwell's equations in vacuum, that means non-interacting electromagnetic fields. There is no matter with which electromagnetic field can interact, so that there is no charge and no density, then all becomes homogeneous equations. Clear? Okay, now look at these 2 equations, 44 and 45. If you want to write this in terms of mu, you can see that you can, that equation 44 and 45 will take this form. You can check this. You know this, right?
Bianchi identity.
Bianchi identity.
That is Bianchi identity, but this is the form of these 2 equations. So this is an identity anyway. This is an identity, mathematical identity. This identity holds because you have taken this form of f mu nu in an antisymmetric way. Because of that, this form satisfies this form. And since these two equations, you can see, if you want to write these two equations, it will take the form of Bianchi identity in terms of F mu nu. That means somehow the information content of these last two equations are already contained in the very definition of F mu nu. Because Bianchi identity, and with this definition, this is just an identity. That means all these dynamic, all this information content of this identity is already contained in this. And since this form is the closed form of this homogeneous Maxwell's equation, that means these homogeneous Maxwell's equations are being taken care of by defining F mu nu by this. Only thing is that to express, we have to only now express these inhomogeneous equations in terms of F mu, in terms of A mu or F mu nu, whatever you call it. And you can check that these two equations you can express in terms of Maxwell's equation, in terms of A mu by this equation. If you want to verify, you just put in this equation, you put the different components of F mu nu and see that you get the first two equations. Clear? And you can also verify that the Bianchi identity gives you these two equations. So this is true only if you define F mu nu in this particular way. Therefore, you can see, so if you want to see what is the equation of motion satisfied by A mu, you can directly say this is the equation of motion satisfied by A mu, where F mu nu is related to A mu nu. You don't explicitly say the other two equations, because this information, this equation in its definition of F mu nu already contains the other two equations. Is it clear?
Okay, sir.
Okay. Now I have to finish. Now, this is the equation of motion of F mu nu or mu. Now, this is the Euler-Lagrange equation for mu, you can say. So, the same Euler-Lagrange equation, this general form, but for mu field, there are 4 Euler-Lagrange equations. So, this should be mu. Sorry. There are small typos, so you correct it. Clear? This is the Euler-Lagrange equation. My question is, what should be the form of the Lagrangian when put here will give you this equation of motion? And you know that this is the form of the Lagrangian. Clear? If you put this form of this Lagrangian in this equation, you will get this equation. So this is the covariant form of Maxwell's equations. Clear? All the information of Maxwell's equations are contained here. Here is also, there is a problem. This should be new. Clear? Now, remember one thing, J is sitting here. What is J? J is rho and J, charge density and current density. They are external to the field, electromagnetic field, where there is a charge density and there is a current density. If there is no charge density and no current density, that means electromagnetic field in a vacuum. That is the status of a free field. The field is free. It is not interacting with any object. Okay. Then Z mu should be 0. Then this term will not be there in the Lagrangian, and this Maxwell's equation will be a homogeneous equations. Clear? Now, again, put the summary of the whole thing, including Maxwell's equations. Here. Look at this. So this is the summary for free fields. So all these things are done. So electromagnetic field, this is the Lagrangian. I dropped the J mu mu term because I am talking about free electromagnetic fields. Okay. And this term is the Maxwell's equation. Clear? So this completes the classical description of relativistic fields. So there are 3 classes of relativistic fields we discussed so far. One is Klein-Gordon field, one is Dirac field. other is Maxwell field. But arriving at Dirac and Klein-Gordon Lagrangians or equations of motion, for that we did it theoretically just from our intuition that a relativistic field should represent a microscopic particle with relativistic speed. For that we need to combine relativity and quantum mechanics. From that standpoint, we constructed these equations of motion, all these Lagrangians, but this somehow nature has already constructed it and presented it from beforehand. Okay. Now, okay, so this ends today's class, but let me tell you, okay, if you have any question, you can ask. I will not teach you because the class notes ends here.
Sir, this is not today's lecture. This is the first lecture on the classical fields. There you have said that when we are considering a classical field, let's say electromagnetic field, so at a given time t, then we have to specify the all special points.
Yes.
X, yes. But
so
you
suppose
have said that we.
Bolo.
But you have said that you have said that we can't fix the spatial space, that is x equals to x1. I asked you the question why.
No, I don't understand. We can't fix the space means?
No, মানে আমি বলতে চাইছি যে স্যার আপনি যখন বলেছিলাম যে electromagnetic field at some point and at a given time, then we need four independent components
at a point in space.
But
so this is mu. At any point in space, at a particular time, at any point in space, you know this. That means at that point of time, at that space, that point in space, you know this. But complete description of this field at a given point of time, at a given time, what is the field configuration in the universe? For that, you need value of this, for that t at all x's. That's what I said. So your coordinates coordinates are a mu x1 t vector, comma a mu x2 t, comma, and all xn up to xn, where all the x's are the different positions. So you are sitting in your room suppose at 10 at this time 12.05. What is the description of the electromagnetic field in your room? The light you are seeing. What is the description of that electromagnetic field? To give that description, you have to, in principle, you have to know what is the value of this a mu at each individual points. Then your description is complete. Now your knowledge of knowing a mu at all points in space at a particular time, that is an infinite list. Okay, that list we don't specify. That we give that argument to show that this field has an infinite degrees of freedom. So that is a system of, if I use a mu as coordinate, in terms of that, this system has an infinite degrees of freedom, because you need infinite numbers to specify one state of the system at a particular time. Now that knowledge you express in terms of differential equations. That is a different thing.
Yes, sir. Okay, clear.
Okay, so one interesting point is to note that ultimately these are all classical fields, and relativistic fields, means their Lagrangians are invariant under Lorentz transformation, and all are free fields. Okay, so only one field is considered. Now, this we are discussing this in the course of particle physics because we want to know what is the how the free quarks and leptons are described. Remember, okay. Now I see that to describe free, I mean this is an intermediate step, intermediate stage where we are stationed just right now. So we arrived that at least since quarks and leptons are relativistic and microscopic, so their description needs relativistic quantum mechanics. For that, these are the Lagrangians. But still, we have not arrived any conclusion how the particle nature of the quarks and leptons, which we observed them in the laboratory as particles, how that particle nature comes from this field. What is their relation? Field is a non-localized entity. At every point in space-time, it has a value. Clear? So field is just a function of space-time, x and t. Here we see the effect of the fields. It's just a value function, value of x and t. So basically, it a space time or একটা jot, the function of x t মানে তো তাই. Clear? It's a knot of x and t. Now, it is not a particle. So somehow we have to come to the particle nature of, so how particle attributes I can be associated, how particle nature can be realized in the context of relativistic quantum, in this quantum mechanics plus relativity. That we have to see. For that we need to quantize these fields. We will show you that, but these are the description of free fields. Okay, but at this level, when suppose something is interacting, these equations represent equations of motions for free fields or Lagrangians for free fields. Not these free field Lagrangians are never observable. Okay, because freedom, I mean, a free particle you can't observe. You have to interact it with to observe. I said this many times. Therefore, these Lagrangians has nothing to do with any physical measurement. Okay, or any physical observation, any real observations should be connected to something which is not a free Lagrangian, which all of these are free Lagrangians, just to, they are making your basis of understanding interacting Lagrangians. Clear? So at some point of time, we have to write the suppose when a Dirac field interacts with a scalar field, or a Dirac field interacts with a photon, how the Lagrangian will look like. Okay. So that thing we have to understand. For that, we are first studying the dynamics of free fields. But there is a catch here, or there is an interesting point here that Maxwell already has given us some hint that if there are Maxwell's equations, if there are charge densities and current densities present in the universe, then Lagrangian has this kind of term. Okay. So there is a J mu here. Okay. We will later see that this is a sort of this is a part of the Lagrangian which must be connected to interactions, because it is J mu is due to something which is external to this field. Clear? Charge and current are external to this field. An electromagnetic field is propagating through vacuum. Suddenly you place a charge, external charge there, or flow current, external current is flowing through that. Then how your Maxwell's equation, electromagnetic field equations will change like this, and Lagrangian will change like this. So this is the interacting part of this field. So we will modify when interactions is present, we will, with free fields, we have to add some term which is the interacting Lagrangian, and that terms are the real terms which can be probed in experiments. We will see that. But remember, I tell you an interesting thing here, that the J mu, suppose, Shaptosha, you are saying that for Dirac field, you derive this current. You will see this is the same current here. When electromagnetic field is interacting with the Dirac field, this Lagrangian modification is like this, where J mu is this. Then this part is a function of psi bar, psi and mu. So this is the type of, then psi bar, this is, I am just taking off the record because this is not taught in course. So this is the form of the Lagrangian that will come when we will study interactions, and this is called QED Lagrangians, and you will see that this Lagrangian contains 3 different fields, psi, psi bar, mu. This is not quadratic in fields. All the other free terms are quadratic in fields. This term. Interacting terms can't be quadratic. They should be, there must be other terms. But okay, this is just for your curiosity, if anyone has, for that I said this, but you may not remember this. We will proceed from this point onwards. But before proceeding, we have to see how under discrete transformations, parity, charge conjugation, etc., these Lagrangians will behave. This we will study when we will at the university, I mean from November after puja. Clear? Is it all right? So I derived all these free Lagrangians. So actually these are for spin zero particles. This is for spin half particle. This is for photon. Photon does not belong to quark and leptons. Okay, so it will serve as a mediator of interaction. So we will see gradually that. Okay. So once you quantize this field, so when you start studying quantum field theory, then you will realize actually what is the physical interpretation of these fields. What is the charge? What is the physical implication of complex and real in terms of particles? Okay, that you will see. All these things. Okay, so we will study first, then when university opens, we will study this C and parity and this charge conjugation transformations of these fields. And then maybe Sanjay will start teaching quantum field theory. And I will also teach some aspects of quantum field theory, which is to fit it with particle physics course. Clear? So if you have any question, you can email me or phone me. So I am okay. So
sir, how do you client?
Client.
How do you know that Klein-Gordon equation is for spin zero particles?
Okay, that we will see. I mean, that we will see. I have not seen this because scalar field. So you can intuitively see it like this way, that a scalar field is just one number, whereas a vector field a mu are 4 numbers. A Dirac field psi are 4 fields with a particular structure. Now, suppose a particle which has no spin. So that means 0 spin. That means it has no other components. If it has a half spin, it can be plus up, minus up, sz. Okay, if it is 1, it can be plus up, 1, 0, minus 1. If it is spin 0, that means it must be single component field. Up to, you can only single component means only 1 degrees of freedom. That's the scalar field. And there are 2 degrees of freedom for this. That 2 degrees of freedom will come because One corresponds to a positive charge, another corresponds to a negative charge. But to actually realize how a Dirac field represents, Gordon field represents a spin zero field, so we have to construct the proper spin operator and then operate on it. I will show this in some class. These are in the part of this course. Okay. But right now you can say that anything which does not have a spin, he has nothing more to specify. Okay, it has only mass. If you have spin, you need to specify some, it has at least two components if it is half spin. So you have to take care of these two components in your Lagrangian simultaneously. To do that, you can't do it with one field, with one component only. So you need some structure, and that structure is inbuilt in Dirac equations, in Dirac fields, and also in Maxwell fields. Structure means at least four components are there. Okay, so, but scalar field is the minimal thing. So when you write a scalar field, it is a phi x and t. But when you don't need any other information there. Just you put x and t, you know phi. But if you want to know what is the Dirac field, just x and t will not give you psi, because just x and t you can put, but then you have four different components. You have to know what is those four different components. Okay. Similarly, if you know x and t, you have to know what are a0, mu, a. So all these four different components of this mu field, or maybe for the structure of this Dirac field, they has to specify some structure, and that structure can come from spin. So you can't a priori say that there will be spin, but for the scalar field, since there is only 1 degree of freedom, it should be spin free, you can say, because spin introduces needs some more components to specify at the same point, at the same time. Because of that, you can safely say that at least scalar field should not talk about spin. Now, how Dirac field and Maxwell's mu fields, they will talk about, they will incorporate spin in them. That is a complicated, that you have to study. But without studying anything, just from the first principle, you can say Dirac field can't have any spin. Klein-Gordon field can't have any spin because it is a single component object. It should have spin zero. If it has a spin more than non-zero, at least two components should be there. Clear? Up to this point, we can say this. Okay.
Sir, which type of particles can be described in the light of real scalar field and complex?
Actually, real. So I give you one example. Say real scalar, that real, we will see later this, but since you asked this question, I tell you that the real corresponds to neutrality, electrical neutrality, and complex corresponds to charge. We will see that. That means if some particle is described by a complex scalar field, that means that particle should carry an electric charge, and phi star will represent that particle. One with positive charge, other say this pi plus and pi zero are actually represented by complex scalar field. I'm sorry. Pi plus and pi minus. Whereas real scalar field is represented by pi zero. All of them are spinless. Okay. Quarks and leptons, all the fundamental particles, quarks and leptons, they are fermions. They are represented by Dirac fields. Okay. Now, for every quark and every lepton, whatever it may be, for every quark there is an antiquark, and every quark can appear in either spin up or spin down. Every antiquark can appear in spin up or spin down, quark or lepton. So any quark or lepton, so spin up, spin down quark, and their spin up, spin down antiquarks, all these four entities are represented by this Dirac field psi, the single Dirac field psi. So all quarks and leptons are represented by Dirac fields. Quarks and leptons are not represented by scalar fields. So in that sense, scalar field does not represent any fundamental particles that constitute nature. only one particle, one fundamental particle, which I have not talked about, which is beyond this, which is not within this classification of quarks and leptons, that is Higgs. Higgs is a classical particle, Higgs is a scalar, spinless particle. It is described by real scalar field, uncharged Higgs.
Sir, phonon, that is the quanta of elastic
phonon is not a particle.
It's not particle. Okay.
Phonon is not a particle in that sense. It is a quanta of
Acoustic waves.
Vibrations. Okay.
Sound force. Sound field.
Sound vibrations. You can see the propagation of sound waves in terms of phonons in that sense.
Sir, it has spin 0. Then what? In what respect it has spin 0?
So you can fit it with this normal structure of these Klein-Gordon equations, but I am saying that it is not a particle in the sense you can't detect it as a free particle. You can't detect it as a particle that way. It does not constitute any matter.
Yes, that was my confusion. Okay.
Hello, sir.
Yes.
So in the case of Klein-Gordon equation, we have seen that rho, the probabilistic interpretation of Klein-Gordon equation is
problematic. Problematic. Yeah, that
So
problem is still there so far as I am talking about in these terms of classical fields. But we will see that problem will go when we will quantize these fields. That we have not studied. But since I know that since when we study quantum field theory, that problem will not bother you anymore. For that reason, we are still studying the features of Klein-Gordon field, though I know that at this level it is problematic. That's why ultimately we have to reject the whole subject of relativistic quantum mechanics because it does not represent because relativity and quantum mechanics are not compatible in this theory. There are many problems in that. There is one main problem that we have not seen. That is the problem with all this even Dirac equation also in combining relativity and quantum mechanics is that when you talk about special relativity, that problem I just bypassed in a way to discuss these things. I have not discussed it, but that problem that I will discuss when I will introduce quantum field theory. But since you asked, this problem is that the quantum mechanics tells you that rho d3, rho is the probability density, rho d3x, rho is minus infinity to plus infinity is 1. Okay. Or for Schrodinger case, rho is mod psi square. For Klein-Gordon case, you can't interpret rho, but for Dirac's case, you can interpret rho as psi dagger psi, if you remember clearly. Okay. So that means probability of finding a system in the universe is a particle in the universe is always 1. Now this is one of the basic principle or one of the basic postulates of quantum mechanics. Okay, particles are indestructible, but in relativity relativistic particles can be destroyed or produced because E equal to mc square relation is operational there. Therefore, if a particle gets annihilated, suppose an electron gets, suppose a scalar particle, say pi or whatever, say Higgs or any particle gets annihilated, so that particle is not there in the universe. When it gets annihilated, its probability density is 0. Then how this relation will be satisfied? So this is not true for relativistic particles. But quantum mechanics says this. So these problems are there because of this you can't work with any further with this relativistic quantum mechanics. It is a wrong theory, to be specific, but still we are discussing these properties of Dirac fields, Klein-Gordon fields in the context of this theory, because once we quantize this theory, these properties will be translated to that. Okay, but it is better to study these properties in this context, because then we will, when we study quantum field theory, we will just see the effect of quantization. We don't have to bother about the properties of these fields. Okay, so ultimately relativistic quantum mechanics, what we are studying, where phi is a relativistic field, these things will go away. Clear?
Okay, sir. Okay.
Okay.
Yeah.
So you রান্নায় তেজপাতা দাও না, আগে রান্নায় দাও, আবার তেজটা নিয়ে তেজপাতাটাকে খাওয়ার সময় ফেলে দাও। আমরা সেই তেজটাকে নিচ্ছি, বুঝেছো তো? তারপর যখন আলটিমেটলি রান্নাটা সার্ভড হবে উইথ কোয়ান্টাম ফিল্ড থিওরি, তখন ওই তেজপাতাটা আর লাগবে না, তার তেজটা আমাদের কাছে চলে আসবে। ক্লিয়ার?
Yes, sir.
ওকে, সো তো ভালো করে পুজো কাটাও সবাই। ওকে, or if you have any questions or any doubts or anything to discuss, you can write mails. Inside, outside syllabus is okay. Okay, ঠিক আছে। ওকে, থ্যাংক ইউ।
হ্যাঁ স্যার, আপনিও ভালো করে পুজো কাটাবেন।
হ্যাঁ, আমি তো ভালো করে, মানে আমার ক্লাস নেই, এই ক্লাস নিতে হবে না, এটা আবার একটু গলার রেস্ট হবে।
হ্যাঁ,
ওকে, থ্যাংক ইউ।
নতুন যিনি আসছে আমার নাম কি? জাস্ট কিউরিয়াস,
নতুন যিনি আসছেন মানে? ও, ওই ব্রহ্মচারীর নাম বললাম।
হ্যাঁ,
সাম মুখার্জি, এখন ওই সামটা আমি ভুলে গেছি। একটা একটা নাম বলেছিল, গুগল সার্চ দেবে তাই বলছো?
হ্যাঁ, আর কি ওই কিউরিওসিটি হালকা।
আচ্ছা, curiosity, just a minute, let me stop recording.